This video will cover the first part of Module 3 for physical science, and this module is on the atmosphere. So what is the atmosphere? The atmosphere is the mass of air, and we're just dealing with Earth, so it's the mass of air that surrounds the planet Earth. So, as we've talked about previously, air has mass, and because it has mass, it presses down. The air that surrounds Earth is pressing down on Earth, and what that means is that at sea level, if we were to take a 1 inch by 1 inch square area, so 1 inch by 1 inch. I know it's not drawn exactly to scale, but 1 inch by 1 inch square. At sea level, there are 15.7 pounds of pressure on that 1 inch part of Earth. So every 1 inch by 1 inch section of Earth has that much pressure pressing down on it from the atmosphere. So that gives us then another term that is called atmospheric pressure. And what atmospheric pressure is what is the pressure that is exerted by the atmosphere. So why don't we feel, if there's that much pressure pressing down on us by the atmosphere, why don't we feel it? Well, the answer to that is, so the atmosphere, the pressure of the atmosphere is pushing on you, but it's pushing on you in all different directions. So because of that, the pressures cancel each other out, and you don't feel the pressure that is being exerted on you. We're going, in class next week, we're going to do experiment 3.1, and in that experiment you'll get to see some of the effects of atmospheric pressure. For now, I'd like to look at a figure with you. And if you can look in your book at figure 3.2, and in your book that is on page 59. And this figure gives us a picture of how a barometer works. So a barometer, in this picture, it basically shows that it is a tube with no air inside, and then that tube is placed into a pool of water. So in that figure you see, so we see something like this in the figure. And then down here, so this is water down here, and this is an empty tube. Well, in that, what the picture shows arrows pointing down like this, and so those arrows are showing that so this is, I should have made this more open here. So this is kind of open, you know, the water is open. So these arrows show that the atmosphere is pressing down on the pool of water. And since there is no air pressure inside the tube, when the atmospheric pressure presses down on this water, that's going to force the water to move up the empty tube. Now, and then as the water fills the tube, its weight is also going to push down, so then you're going to get this. So the weight of the water is going to push down, and that fights against the pressure of the atmosphere. So at some point, the water, as the water rises in the tube, the weight of the water in the tube is going to equal the pressure of the atmosphere that's pushing the water into the tube. And then the water will stop rising, and that will give us the atmospheric pressure. So if the amount of pressure in the atmosphere is high, so if we raise the amount of pressure, maybe I'll can make this. So if the amount of pressure that is in the atmosphere is high, and we'll illustrate that by big arrows. Okay, so if the amount of atmospheric pressure pressing down on that water is very high, well, that's going to force the water to move farther up that tube, and therefore the barometric pressure would be higher. If the amount of pressure, if the atmospheric pressure is lower, then we would see the opposite effect. So if you have a low atmospheric pressure pressing down on that water, then the water is going to not be forced up as high, and the barometric pressure would be lower. So barometer is just an instrument to measure the atmospheric pressure. And the reason that this is important is that when weather patterns change, the atmospheric pressure changes. So we use barometers to predict, as one way to predict and track weather. So usually when you hear a weather report, they will usually report the barometric pressure and also will indicate whether the pressure is rising or falling, because that can be used to indicate and predict weather patterns. We usually measure atmospheric pressure using the element mercury. And the reason for that is that mercury is very dense, and if we were to take an average atmospheric pressure, at an average atmospheric pressure, mercury would rise about 30 inches. So if we, instead of water, if we had mercury in this tube, which is what most are made of, if we had, the abbreviation for mercury is Hg. If we had mercury in this tube, and if we had an average pressure, the mercury would move up that tube about 30 inches. And the reason we don't use water is that because water is not as dense as mercury, the same pressure that causes mercury to rise 30 inches would cause water to rise 33 feet. So obviously you'd have to have very, very tall columns of water to measure just an average atmospheric pressure. So barometers use mercury rather than using water because of that. So usually barometric pressure is given in inches. So usually given in inches. And again, it would be, how many inches does the atmospheric pressure cause that column of mercury to rise? So on the news, you might hear something like 29.9 inches as the atmospheric pressure. If we were to use the metric system, so the metric system, usually the units that would be used would be millimeters. So how many millimeters does the pressure of the atmosphere cause the mercury to rise? And an average atmospheric pressure, if you're using millimeters, is 760 millimeters. And so usually the way you will see this written is you will see 760 millimeters, and then you would see the symbol for mercury. So 760 millimeters of mercury is how far in the barometer tube the mercury would rise at an average barometric pressure. So when another unit that we use to report pressures then is an atmosphere. And an atmosphere is abbreviated as 1 ATM. Okay, so that's the abbreviation for the average atmospheric pressure. So this would be equivalent, 1 atmosphere is equal to an average atmospheric pressure 29.9 inches, or it's also equal to 760 millimeters of mercury. So 1 atmosphere is just an average atmospheric pressure. So then what we do is that we report the atmospheric pressure then as what part of 1. So if the atmospheric pressure is lower than average, instead of being 1, it would be 0.9. So in other words, this would be 90% of an average atmospheric pressure. So in other words, it's slightly below average atmospheric pressure. And on the other hand, we might say that the atmospheric pressure is 1.1 atmospheres, and that would mean that it is 110% of the average. So in other words, it's 10% higher than an average atmospheric pressure. Okay, let's go ahead and look at a couple on your owns in your book. So let's look at on your own 3.1. So that one says, in general, should atmospheric pressure increase or decrease as altitude increases? So as you go to a higher altitude, so as you go from sea level to areas like mountains that are, above sea level, so altitude, as you increase the altitude, the atmospheric pressure will decrease. So with increased altitude, you're going to get a decrease in the atmospheric pressure. And that should make sense to you because, you know, as you're higher, the amount of pressure that's pressing down is going to be less. So decreased atmospheric pressure with an increase in altitude, because there's less air. As you get higher up, there's less air pushing down. Okay, then let's look at the On Your Own 3.2. So On Your Own 3.2 says that the atmospheric pressure is 1.1 atmospheres. Which of the following values for atmospheric pressure would you see in the weather report? Okay, so remember that we said that 1 atmosphere is equal to 29.9 inches. Okay, so what would 1.1 atmosphere be? And our choices are 29.9 inches, 32.9 inches, or 28.1 inches. Okay, so this tells us that the pressure is above average. So if average is 29.9, so we can eliminate this one because that is average atmospheric pressure. That's 1 atmosphere. So this was 1 atmosphere. We look at this one and it is above 1 atmosphere. So this would be our correct answer. And the reason this one is correct is that this would equal less than 1 atmosphere. Okay, because if 1 atmosphere is 29.9, then obviously 28.1 inches is going to be less than 1 atmosphere. So the answer there is 32.9 inches. Okay, the next topic that we are going to discuss is that the fact that Earth's atmosphere is in layers. We divide Earth's atmosphere into 2 primary areas. The first is called the homosphere, and the second is called the heterosphere. Of where so the homosphere, this is the air that we breathe, and it's called homosphere because the distribution of the gases that make up the air in the homosphere will always be the same. So remember that we said that 78% of the air that we breathe is nitrogen, 21% of the air that we breathe is oxygen, and then about 1%, the remaining 1% are other gases. So it doesn't matter where you go in the homosphere, the air that you breathe will always be 78% oxygen, 78% nitrogen, 21% oxygen, and 1% other gases. Now, as you go to higher altitudes, we've already said that there will be less air, but there will be less air, but the air that is there will still be 78% nitrogen, 21% oxygen, and 1% other gases. So it's called homosphere because even though the amount of air might change, the higher you go, the percentages of the gases that make up that air stays the same. So the homosphere exists from the ground up to about 50 miles above the ground. And then the heterosphere, it exists above 50 miles. So it sits on top of the homosphere. So anything above 50 miles above the ground is the heterosphere. So let's look more specifically at the heterosphere. So hetero means different. And so what the heterosphere tells us is that what the air is made up of depends on the altitude. So in the heterosphere, in the lower part of the heterosphere, it's mostly oxygen. And then above that, you get helium. It's primarily, you get, it's mostly helium. So if we breathed this air, you would talk funny if you ever breathed air out of a helium balloon. And then at the highest level, it's mostly hydrogen. So again, compared to the homosphere, you see that the gases change as you move to different parts of the heterosphere, whereas it's always the same no matter where you are in the homosphere. And remember that in the homosphere, there is nitrogen and argon. Well, in the heterosphere, there is very little nitrogen or argon in the heterosphere, but we saw that in the homosphere, 78% of the homosphere is made up of nitrogen. So heterosphere, the gases change depending on where you are in the heterosphere. Okay, let's look at on your own 3.3. So on your own 3.3 says that in chemistry, mixtures are classified as either heterogeneous or homogeneous. Based on what you learned about the difference between heterogeneous and heterosphere and homosphere, is milk heterogeneous or homogeneous? Well, milk would be homogeneous because if you think about a glass of milk, the components of that milk are evenly distributed throughout. Every drink of milk that you take would have the same distribution of fat and water and protein. So milk would be considered homogeneous. What about salad dressing? Well, salad dressing is made up of vinegar and oil and usually some spices. And if you, even if you shake the salad dressing really well, when you squirt it onto your salad, every squirt is probably going to have a different composition of the oil and the vinegar and the spices. So salad dressing would be considered a heterogeneous mixture. Okay, and then let's look at on your own 3.4. And 3.4 says if an airplane travels at an altitude of over 4 kilometers, it is required to have a special oxygen supply for the pilot. As you just learned, that altitude of 4 kilometers is well within the homosphere. So 4 kilometers is within the homosphere. So why would the pilot be required to have a special oxygen mask at that altitude? Well, remember that even though the percent of the air is still 21%, the oxygen is still 21%, but as that airplane climbs to a higher altitude, there's going to be less air. So 21% of less air means that there's going to be a reduced amount of oxygen, and therefore the pilot is required to have that special oxygen mask. So let's go ahead and look at a figure here. It will come up. I was going to show you figure 3.3 in your textbook, and that figure basically shows what we just went over. It shows the homosphere that is made up of 78% nitrogen, 21% oxygen, and 1% other gases. Then it shows you the different areas of the heterosphere, the lower part being primarily oxygen, and then above that it's going to be primarily helium, and then above that primarily hydrogen. So it's very clear from that figure why the heterosphere is called the heterosphere, because the concentration of gases is different in different places within the heterosphere. Okay, so let's look now at the homosphere, and we're going to look at the areas that make up the homosphere. Okay, so remember the homosphere is from the ground up to about 50 miles. So this is the air that we breathe. And the homosphere is divided into 3 areas. And the 3 areas that make up the homosphere are the troposphere, the stratosphere, and the mesosphere. Okay, so let's look at each of these. So the troposphere is from the ground to about 7 miles above the ground. The stratosphere is from 7 miles to 30 miles above the ground. And then the mesosphere, the mesosphere then is from 30 miles to 50 miles above the ground, because then above that you would have the heterosphere. 30 miles to 50 miles above the ground, okay? So remember that we said that the higher you go, the amount of air decreases. So as you go to higher altitudes, the amount of air is going to decrease. And so that means as you go from the troposphere to the stratosphere to the mesosphere, the amount of air is going to be decreasing as you go through those areas. So there is more pressure, there's more pressure in the troposphere and less pressure in the mesosphere. So what we would say that the mesosphere is thin air, just because with less pressure there's going to be less air pressing down. Okay, so let's start by looking at the troposphere. And if you want to, as we're talking about this, it would be good for you to be looking at figure 3.5. So look at figure 3.5. And as we're talking about these different areas, you can locate them on that figure. So the first one we'll talk about is the troposphere. And the big idea about the troposphere is that this is where weather occurs. So whether we are talking about, so this is where the clouds are, the rain, snow, lightning, etc. All of that happens in the troposphere. And the other thing is that most of Earth's air supply is in the troposphere. And again, remember, it's because you have more air, and then that air is, 21%. All of that air is 21% oxygen. So about 75% of all of Earth's air is within the troposphere. And we've already said that within the troposphere, the amount of air decreases as you increase altitude. So if we think about a place like Mount Everest, so Mount Everest is 29,000 feet above sea level. So at that altitude, the air is still 21% oxygen, but there's much less air. So most people, the vast majority of people who are climbing Mount Everest, there have been a few people who do it without breathing oxygen, but the vast majority of people who are climbing Mount Everest are doing it by using oxygen tanks, supplemental oxygen. Most of us aren't going to be climbing Mount Everest, but many of us go to a city like Denver, Colorado, which is called the Mile High City. And a mile is 5,280 feet. So Denver, Colorado is 5,280 feet above sea level. And the air, there's about 90% of the air in Denver as there is at sea level. So that, and this is enough of a difference in the decrease in the amount of oxygen that is available that athletes do feel the difference when they compete at these altitudes. So even within the troposphere, up to 7 miles, you will see decreases in pressure as you go to increasing altitudes. The other thing that will change within the troposphere is that as you go to higher altitudes, the temperature will decrease. And you may, if you've climbed mountains, last spring, my husband and I went to the Smoky Mountains, and we hiked up to a part of the Smoky Mountain that's called Mount LeConte, and even as we hiked that mountain, which is not a very high mountain, we could feel the drop in temperature that occurred as we got to the top of that mountain. So within the troposphere, as you reach higher altitudes, the temperature will decrease. So this is why there are some places, if you go to places where there are mountains, you can sometimes still see snow on the mountains. And when you're at the foot of the mountains, there's no snow, but you can see the snow at the top of the mountains. And that's because with increasing altitudes, there will be a decrease in temperature. Okay, so that's the troposphere. Then the next area that we'll go ahead and talk about that makes up the homosphere is called the stratosphere. So remember, the stratosphere exists from about 7 miles up to about 30 miles. So 7 miles above sea level to 30 miles. So in the stratosphere, there is no weather. Okay, so this is above the area where we see any weather. There may be a few clouds at the lowest level of the stratosphere, but very few. And the air within the stratosphere is very dry. So remember, we talked about the relative humidity, or the air within the stratosphere. The air would be very dry. The other thing that you see in the stratosphere are these winds that are called the jet stream. So they are steady winds that circle the Earth. So steady winds. These winds are blowing up to about 250 miles per hour. And they blow from west to east. So these winds blow at the top of or above the clouds. So they do affect weather, and they steer the storms, and they also affect how pressure is different in different areas. So often when you listen to a weather report, they will give information about the jet stream, and you probably also know that most weather patterns come from the west, and that's because these jet stream winds blow from west to east, and they steer weather patterns as they are doing that. Okay, so now a thing that we see, the thing that is different in the stratosphere now is that in the stratosphere, as you go to increasing altitude, the temperature decreases. So with increasing altitude, you actually see I'm sorry, I said it decreases. The temperature actually increases. So that's, so it gets warmer as you go to higher altitudes. So at the bottom of the stratosphere, so at the bottom of the stratosphere, the temperature is about negative 85 degrees Fahrenheit. But when you get to the top of the stratosphere, the temperature is about 37 degrees Fahrenheit. So with increasing altitude, the temperature actually increases, it gets warmer. And the reason for this is something we talked about last chapter, and that is the ozone layer. Because the ozone layer is, it exists within the stratosphere. And remember, the ozone protects us from UV light. So it absorbs that UV light, and that UV light has energy. So this layer is actually absorbing energy from the sun. And since that layer is located within the stratosphere, that increased energy that is absorbed from the sun is going to lead to an increased temperature. So within the stratosphere, as you go higher, the temperature is actually going to be getting warmer. Okay, then the last area within the homosphere is called the mesosphere. So this exists from about, I'm going to give it to you in miles. This exists from about 30 to 50 miles above sea level. So 30 to 50 miles above the ground at sea level. So within the mesosphere, you're going to have very thin air. And now we again, because the ozone layer is not in the mesosphere, now temperature will decrease as you go higher. So temperature decreases again with increasing altitude. So just like in the first layer, so now we're back to what it was like within the troposphere, where it gets colder as you go to higher altitudes. So that by the time you get to the top of the mesosphere, the temperature will be about negative 150 degrees Fahrenheit. So remember, at the top of the stratosphere, we said it was about 37 degrees Fahrenheit. And then by the time you get to the top of the next layer, the temperature has dropped to negative 150 degrees. And that's because there's not as much ozone, and so the temperature is going to drop off again. Your book has a little bit of a discussion about where airplanes fly that you might be interested in. So the thing that airplanes have to think about is that as they go to higher altitudes, so at higher altitudes, because the air is more thin, so at higher altitudes, the air is thinner, and that means that they can fly there. They use less fuel because you don't have as much air resistance. However, but it costs fuel to get up, to climb to those altitudes. So remember last chapter, so it uses a lot of fuel to climb to higher altitudes. So remember last module, we talked about the cost-benefit analysis. So what commercial airlines have to do is they kind of have to weigh the benefit of, yeah, you can fly at higher altitudes using less fuel, but it also costs you a lot of fuel to get there. So they have to kind of weigh that. And typically airplanes will fly from about 5 to 8 miles above Earth, because they have figured out that at that altitude, the fuel that they burn at 5 to 8 miles is less fuel than it would cost them to climb to a higher altitude. So commercial airlines usually fly within about 5 to 8 miles. Now, so that's commercial airlines, but they're supersonic aircraft, so that means that they are flying above the speed of sound. So supersonic airplanes, because they are able to go at a very fast speed, they travel most efficiently where the air is thin. So supersonic aircraft will usually fly within the stratosphere, because they can go so fast that they are able to fly at those altitudes using much less fuel, and it compensates for it overrides the amount of fuel that they needed to climb to those altitudes. Okay, let's finish up by looking at 2 on your owns. So the first on your own that we'll look at is on your own 3.5. And that one says a supersonic jet travels in the stratosphere. If such a plane were flying over a region that is experiencing thunderstorms, how would the supersonic jet be affected? Okay, so what you need to remember about that is that there is no weather events happening in the stratosphere. So if the plane might be flying above an area that's experiencing a thunderstorm, but it's not going to be affected by that thunderstorm because it's flying in the stratosphere, and all weather is in the troposphere. Okay, and then on your own 3.6, that question says, water freezes at 32 degrees Fahrenheit. So 32 degrees Fahrenheit, water freezes. Suppose you were able to watch a sealed vial of water travel up through the homosphere. It would freeze once it got to about 5 to 7 kilometers high. Would the frozen water ever melt as the vial traveled further up? If so, where would this happen? Okay, so we've already said that in the stratosphere, as you go to higher altitudes, temperature increases. So temperature increases, gets warmer as you travel through the stratosphere. So when another thing you could do is you could look at figure 3.5, and you will notice that near the top of the stratosphere, you can see that the temperature rises above freezing. So you can see the temperature near the top of the stratosphere is 40 degrees Fahrenheit. So near the top of the stratosphere, the temperature would be above freezing, and the water would melt at that point. So near the top, temperature is above 32 degrees Fahrenheit, and so the water would melt at the top of as it got near the top of the stratosphere. And then remember, once you get into the mesosphere, then as you go to higher altitudes, then the temperature begins to get colder. The temperature begins to drop again with higher altitudes. Okay, so that is the information for the first part of Module 3 in physical science, and we'll finish up the next part next week.